figure out kind of what's up with the types of answers that we get, and even the amount of answers that we get when we kind of like consider these kinds of statements. Now, this is Mathy lesson number 3. This is sort of the third one. So hang in there, do a nice job, but hopefully we have some fun stuff for you. But I'm just being honest, again, some mathy stuff also. And, you know, you have these statements, which if you're like, what am I supposed to do here? Well, you would solve them. You would solve them. And all I'm really, what I'm trying to do here is say that we have different methods for solving these. And sometimes when something's easy, we kind of forget, oh, I mean, I can just do the inverse. Yeah, you can just do the inverse. The reason I'm choosing that method right now is because I want to kind of throw the question out, why is that the answer that we get when we do the inverse? Is it like the first answer? You know, why is that the one that we get? Okay, if you say, what do you mean the one that we get? Well, if you would do this problem with a graph, you would realize that there's different places that equal -1/2. And something that we did do late last week, we talked about many places that equal -1/2. But why is the one that my calculator spits out the one that is, what was it again, -30? Is it the first answer? You know, is it the positive answer? Obviously, it's not the positive answer, but you got to kind of stay tuned, and we'll give you a good reason. How about this other one? If I was going to try to do cosine equaling -1/2, of course, I could do the inverse, and I get that answer. And again, my whole point here is really just to ask, well, why is it that one? Again, is it the first answer? Is it the positive answer? I mean, it looks like it's an answer way out at 120. Okay, and really the reason that your calculator gives you these values has to do with something that is this idea of principal values and inverse trig graphs. Okay, we got to sink into this idea of principal values and inverse trig graphs. And our goal is that you'll know why we end up with these answers and why really there's only one answer. And there'll be a couple other things mixed in here also. Now, your very own sine wave. Your very own sine wave. It actually would make for good hanging, right? Somebody said they're going to like hang it on their fridge. I would say, why don't you hang it on your trigonometry? It would be a great ornament on your trigonometry. Now, speaking of your trigonometry, what would be at the top of the tree? What would be at the top? The unit circle. Okay, perfect. Up there at the unit circle. You could hang the sine wave. Now, you could also hang the cosine wave. Just string some popcorn, and you get the cosine wave. You thought that was some kind of like Pennsylvania Dutch tradition, but no, you're actually graphing or hanging the cosine wave in your trigonometry. What else? What else could be in your trigonometry? Well, you could put like a drum, like sort of a drummer boy, but yeah, it's SOHCAHTOA. So you could put SOHCAHTOA on there, a little drum ornament. And there'll be some other ornaments that will hang and that I can give as a corny joke later in a few weeks. So get that trigonometry kind of ready this year. Now, question about the sine wave. Question, is this a function? Is this a function? You should be saying, yes, Mr. Naylor, it's a function. Okay, now that kind of goes back to some Algebra 1, Algebra 2 stuff. Remember, this is a function for a couple reasons. It passes the vertical line test. Okay, the vertical line tests would only touch at one point. Why else is this a function? Each x as you go along this graph has how many outputs? 1. Okay, so this has been a function since day one. We like functions in math, okay, because they behave. They behave. Now, What I want to show you today, for sort of the first time ever, is the inverse of this graph, the inverse. And from Algebra 2, or just as something to learn today, but you would have been told this before, the inverse of any graph is always the reflection over the line y equals x. See that diagonal line on your paper? That's y equals x. Y equals x is that perfect diagonal line that if you fold, you will get the inverse. Okay, now you're saying, should I fold it? Well, we're going to in a second. But if you would fold your graph over the diagonal line, you create the inverse. Now, to help you to do this, what I want you to do is to get your paper ready to do a little carbon copy. Now, to get your paper ready to do a little carbon copy, you just have to, with your pencil, trace the sine wave. What you're really doing here, folks, is you're putting like some graphite on your paper. So make it thick and sloppy. Get a nice thick glob of graphite over top your sine wave. Again, the reason you're doing this is ultimately so you can make a little copy. It doesn't work usually with pen because the pen seems to dry.
You're doing the whole thing.
Yeah, I would trace the whole thing. Now, when you're ready, you're going to reflect. You're going to reflect this graph over the line y equals x. If you're like, sounds good, but why are we doing this again? Because remember, when you fold or reflect over a diagonal line, you get the inverse. And trust me, you're going to want to understand the inverse today. So fold it carefully when you're ready over the diagonal line. Now, there's different ways to get like a little copy to show up. Okay, it all depends on the student, the pencil, and maybe a little bit of luck. One of the ways you can get this to work is just to kind of do this. You know, you're sort of just rubbing the pencil. Okay. If you open it up and you don't see anything, then you need to press harder by doing this. This is usually what kids need to do. You have to press harder by actually tracing the back of your paper, because what that's doing is just pushing down that graphite. So figure it out a little bit. Trace the back of your paper. You're pressing down, which is leaving an imprint. You actually will have to flip it on both sides, and you'll have to trace or press down. You can't really mess it up. If you open up the paper and you don't see anything, then you didn't trace the right spots. When you open up your paper, you should see the graph in a reflected place. And you can just trace the back of your paper to try to get it to press down. Listen, you're making the inverse right now. You're making the inverse. When you open up your paper, you should see the graph in a new place. It should be connected. So if there's like a missing spot, you can fold your paper again and do it and keep tracing. Looks good. Sometimes people will then copy that graph. If you have a different color in your arsenal, you could trace over it with a different color, or you could just look at it and say, that's the inverse. Any issues? It looks like we're getting some success here. Good. So again, that is the inverse. Now, I hope you don't look at it and say, it's the same. It's not the same. but it is similar. I mean, it came from the sine wave, but let's be careful about maybe some conclusions we might start to make. It's not the same. Okay, but again, it is the inverse. In a moment, we'll go to the next step here in this little conversation. I don't know if I would write anything down yet. Just hold off a second. I'll maybe give you the heads up when you could write something in your notes. Now, are you ready for sort of question number 2? Just something to think about kind of mentally here. Is the inverse a function? Is the inverse a function? Okay, good. You should be saying, no, Miss Naylor, that is not a function. In fact, it fails miserably, right? It's miserable. If you start drawing vertical lines, man, you're touching points all over the place. And you know this graph keeps going, and so my vertical lines are going to keep touching. And so we have a big problem. We have a big problem. Because in math, we don't like things that aren't functions. Why? Because they misbehave. They misbehave because they give too many answers. Okay, so what we're going to do is we're going to fix the problem. Now, because the language here is a little bit technical, bless you, I have the question up on the screen. I still don't know if you need to copy it down. You can copy anything you want, but make sure you think about the question. Okay, because what I'm going to ask you to think about is how you could restrict the original sine wave so that the inverse would be a function. Now again, are you thinking, whatever it sort of takes for you to do that, maybe you're saying, not sure I get it, so I'm going to just paraphrase it. I think everybody knows that the yellow graph came from the original graph, okay? But what we want to do is we want to restrict the original graph. What that might imply is I want to erase some of it, because that in turn would erase some of this. How could I restrict this? How could I get rid of some of this? How could I erase some of this so that I would in turn get rid of some of this? What do you think? It's always nice to hear from you, so go ahead.
Does it have to do with the period?
Okay, does it have to do with the period? Do you sort of have a favorite part of the sine wave? Maybe like the positive period?
No, I mean, oh wait, I meant like in that, but like if we stretch it out, not the period. What's that called? No.
That'd be the period.
Yeah.
Okay, now it might not be exactly what you were kind of suggesting here. I can see a little bit in your brain that you were thinking about changing something here, but let's just go with this because it'll be good for the learning piece. We erase the negative, whether maybe that was what we want to do or not. So I'm going to erase.
Now we're only going up and all
Well, that would be what this restriction would have done. If I restrict and only have this, now I only have this. How we doing? How we doing? Is this a function? Not quite, but like better, right? But not quite. Good.
Is there a way you could like cut off the, I don't know how to say it, like a straight part that goes through 180? Is there a way you can just keep that and erase everything else?
So now, are you talking about like just keep this part right here?
Yeah. When it curves around, it's going to curve.
Okay, so I just erased, like kind of how you said there, the part that curves around. I think, wait, 180, oh, it would go to here. Okay, so I actually cut off that little piece. Or do we want to get rid of all this up to there? So you have just this straight part?
Is that on the bottom graph?
It's okay. Nobody maybe is sure, but I'm just sort of following your directions. Is that a function now? Oh, it is. It is a function. So, okay, you did successfully kind of cut off. And what I'll add to this is that there's no reason that you would know this, but instead of taking this straight part, which again, nice job. Instead of taking that straight part, we actually will choose to take this straight part. Now, again, there's no reason that you would know except that it's, as was said, kind of the straight part. But if you take this part, now I got to recreate my graph again, you're going to end up then in this, well, it's going to be called the principal region. This is the principal region. And what we want you to realize, at least right now, is that it is a function. This yellow graph is now a function. And because it's a function, well, let me rephrase that. Because it's restricted, we use some new notation. And the notation is that it's going to use a capital letter. In fact, this one up here is also going to use a capital letter. And you're probably feeling like you want to write something down now. I'm going to show you something up here, which you'll probably want to grab. But let me just kind of say it again, because sometimes people are like, wait, what just happened? We now have a restricted region. We have a restricted graph. It's called the principal region, and it's denoted with a capital letter. And it made the inverse a function. Now that's a mouthful, so let me give you some text that you might now want to jot down. And we'll draw these graphs. If you're like, I want to draw this graph. Yeah, we'll draw them. I just want you to take stock of what we've done here. What we've done is we have made a restricted graph. It's called the principal region or the principal values. It's denoted with a capital letter. So that's kind of new. Like if you see a capital letter, it's not because it's the beginning of a sentence. But when you have this principal region, it's a restricted graph. And honestly, the big kicker here is it makes the inverse a function. That should be big and bold. It makes the inverse a function. Now these places, and again, I really like how you said it, kind of like only takes sort of this straight part. It's really kind of peak to peak. And for sine, it's negative 90 to 90. If you look at the graph, you would say negative 90 to 90. And when you guys finally make the connection with me, you'll realize that that's also where your answers, like on the calculator at the beginning of the period, that's where those answers also come from negative 90 to 90. Okay, and the reason those two numbers are special is because if we go down here to the inverse, it's now a function. Okay, and again, we like functions because they only give one answer. We're going to end up drawing all of these. I'm talking about principal sine, principal cosine, and the principal tangent. So if you kind of want to organize your notes that you can have all three of these. I don't have a cute little paper for you to fold, but you can still kind of think, what would this look like if we did fold it? There's your cosine graph, just kind of dotted because we're only going to end up taking some of it. maybe I ruined your fun here by drawing this cosine graph. It's a little harder to visualize, but indeed, if you do fold the original graph diagonally, you end up with this snake, okay? Which, of course, is not a function. And so we're back to kind of the same place. We want to do some restricting. It turns out that the restricting, in the same manner, only needs to go peak to peak, kind of the, quote, straight part. And so for cosine, it turns out that that happens here. It happens from x equals 0 to x equals 180. X equals 0 to x equals 180. Remember that problem at the beginning of the period? Okay, the answer was 120. That's because the inverse is only going to require these numbers. So my inverse is now a function, which is only this solid part of our principal graph. Okay, so again, from 0 to 180, you end up with the principal values. And I didn't show you a tangent, but sometimes with a little bit of visual observation, you can deduce its principal region. Now, tangent has always had asymptotes. Recall with me that they're at negative and positive 90. Somebody says, should I kind of have that memorized? Well, yeah, you should have knowledge of that. Maybe it's something you kind of have to study and brush up on. But tangent has always had a period of 180 between negative 90 and 90. Now, do you realize whenever you fold something diagonally, this is just a little bonus for coming to class today. Whenever you fold something diagonally, it actually switches vertical to horizontal or vice versa. These problems over here were kind of horizontal, and when they folded, they became vertical. This problem is vertical, and when it folds, it becomes horizontal. So that always happens when you fold over a diagonal line. Well, now, I'm drawing only the restricted part right away. I'm drawing the principal part. So you know that it would have another part, another part, another part.
So you only do one period.
That's correct. For tangent, you only do one period. Be careful. I didn't say that for these other ones. In fact, the truth is it's half a period for these other ones. But for tangent, it's one period from negative 90 to 90. Okay, so that I only end up with one inverse. So I only end up with one wave for my inverse. Now, that's kind of the mathy part, like the theory. And if you're like, what's the theory? The theory is I don't want all of a sine, cosine, or tangent because I want the inverse to be a function. You say, well, why do you want the inverse to be a function? Well, because when you start applying this, when you start doing a math problem, you only want one answer. Okay, that's usually the way math works, where you input expecting to get one output. So let's kind of do a math problem. Now, it's still a little mathy because look at this notation, okay? You'd have to have knowledge of a couple things here. First of all, you see a capital letter from just being here for the last 30 minutes. You say, okay, that means something. That means principal. Okay, well, that's correct. And what that also means is you're only going to get one answer. Now, when you get this one answer, it's going to be an angle because, remember, this is an inverse problem. It's just an inverse problem sort of disguised with that arc symbol. So where can you do an inverse problem? Well, on your calculator using the inverse button. Now, this is kind of one of those things where sometimes people are like, is that it? Is that all this is? You know, there's got to be a catch. But I want you to understand that when you do the inverse on your calculator, and you've done this since SOHCAHTOA, right? And you did it, just recently maybe to get some answers on that practice paper. But when you do that inverse button, you are already getting the principal answer. Your calculator is in principal mode. Like, it would be kind of weird if when you hit enter that a whole list of answers came out. You sort of wouldn't have expected that. That's because your calculator is already giving the one principal answer, which, by the way, the one principal answer is right there. It's not the one over here. It's not the one back here. It's the one principal answer right there. But it's almost too easy. You just put it in your calculator. I'm serious. You can just put it in your calculator. How about the principal inverse sine of root 2 over 2? Again, if you see that notation, it's kind of like giving you permission to just put it in your calculator. Okay, because your calculator is already in principal mode. It's already outputting the one principal answer. Now, you're not going to get like 10 of those to do. That'd be boring. You do 2 of them, 3 of them, you get the idea. But I want you to get the idea that it's only giving the one answer, again, that's in this principal region. I'm pointing right there because that would be like 45 degrees. Okay. Now, you could do this with a graph. Like, you could graph the sine wave. You could trace to root 2 over 2. Okay. But you're only going to be confirming what your inverse button already told you. Okay. So is there a graphing method to this? There could be. Or you could just do the inverse. Again, like we did right here. Well, it's a little extra here. You might notice that I've never did this. I've never graphed the inverse in the calculator. That's because just like we switched the numbers up here, we switched them, you would have to switch them in your window. And it's a little bit of stuff we don't need to do, but since you asked, if I really want to do this, I would have to switch my X and Ys, okay, because they always switch whenever you do an inverse. In other words, I would have to do something like this. But honestly, Owen, there's never a time where you need to get your calculator to do that. But no, that's this. You're not. It's a good question. You're not, because they would just be the reciprocals of these anyway, so we could always go back to these. But ultimately, you won't. Don't worry, you won't have to do that. Now, I don't know. It depends on how much you remember that Miss Naylor says. I hope you remember what I say, but sometimes, you forget. But I've said a couple times that we were going to answer the question why, when you do a composition, you only really need to focus on quadrant 1. You only need to focus on quadrant 1. Let's do this problem, kind of like we had not had today's lesson, because you still would draw a triangle that has a y value of root 3 and an x value of 1. And you would hopefully quickly say, okay, 1, 2, root 3. Now remember that you would have to do the cosine of this whole triangle. And of course, that's x and y. Check that, that's x and r. So we would end up with 1 over 2. So, why are we only in quadrant 1? Whenever you combine functions together, there's an overlap. And it's kind of like saying you're only allowed to use the overlapping regions. What I'm really talking about is the overlapping principal regions. Now, sine goes from -90 to 90. So does tangent. Okay, but cosine goes from 0 to 180. So I guess what I'm trying to suggest is, where do these regions overlap? Well, the answer is in quadrant. Take a look at this little diagram here. I spent a few minutes doing this. Sine and tangent are from -90 to 90. Cosine's from 0 to 180. So again, where do those angles overlap? Okay, and the answer is in quadrant 1, from 0 to 90. 0 to 90 is kind of the only safe place. Listen to this. It's the only safe place when you're combining trig functions. So when you're combining trig functions, I have to go to the place that they share. It's always going to be 0 to 90. So that's why you put them in quadrant 1. Why do we even have this lesson? Why do we have principal values? This is actually a test question, if that gets your attention a little bit. This is also a nice closing question for the lesson. Why do we even have this discussion? And it's a little fill in the blank. Do you want to maybe share with your neighbor? Do you think that they're thinking of the same fill in the blank? There's 2 words you're going to use. You're going to use
Inverse.
and, right. Okay, we want the inverse to be a function. Okay, we want these yellow graphs to be functions. Your homework, it's kind of different. It actually summarizes the lesson. You might even feel like it's kind of like reteaching the lesson. Yeah, go through the homework and let it sort of summarize what we talked about. Don't forget to take your little sine wave along for your trigonometry.